In this video, we'll introduce separable equations. A separable equation is a first-order differential equation in which the expression for dy dx can be factored as a function of x times a function of y. In other words, it can be written in this form: dy dx equals g of x times f of y. Notice that on the right side we have two different functions. One is in terms of x, the other is in terms of y. In this example, we have dy dx equals g of x over h of y. Very similar to what we have up here, only this is multiplication and down here we have division. But notice you have g of x in terms of x and h of y in terms of y. Our goal is to separate these and have the left side be in terms of y and the right side be in terms of x. Focusing on this example, we can push all variables y to the left side and all variables x to the right side. We can do that by cross multiplying. We'll get h of y dy equals g of x dx. Notice now that the y's are on the left and the x's are on the right. Next, we'll integrate each of these. From there, we can solve the equation. In our first example, we have dy dx equals 3x squared times y squared. The goal is to put all terms that involve x on the right side and all terms that involve y on the left side. We do that so that we can separate these two functions. We'll need to divide both sides by y squared, and at the same time we can multiply both sides by dx. That will give us dy divided by y squared equals 3x squared dx. Notice at this point, y's are on the left, x's are on the right. If you want, we can rewrite that left side 1 over y squared dy equals 3x squared dx. Not super necessary, but sometimes I like to see it written like that. Next, we will integrate the left and integrate the right side. Integrating on the left, we get negative y raised to the negative 1 plus c. And I'm going to call that c1 because we're going to have a constant on the right side as well. Integrating on the right side, we'll get x cubed plus a constant, which we will call c2. Next, I'm going to just rewrite that first term as negative 1 over y. And typically, I'm not going to have these two constants because we can combine them into a single constant. So in the future, I'm just going to do that on the right side and call that right side constant c. These are, again, just two arbitrary constants. We're going to combine them into a single constant. So I will not show this step every time. I'll just put the c's on the right side in the future. Now let's see if we can solve for y. We'll get y equals negative 1 divided by x cubed plus c. Note that we also have y equals 0 as a solution. When solving, up here we divided by y squared, which assumes that y is not equal to 0. So we still need to check to see if y equals 0 works. And we can do that. We can look at dy dx and let's see what happens if we make it 0. We'll have 3x squared. Y, again, we want to be 0 squared. And we're asking, is that 0? We'll see that 0 equals 0 is true. So since that's true, we can say that y equals 0 is indeed another solution. It does satisfy the differential equation. In this example, we again want to solve the equation by separating the functions. The first thing I'll do is rewrite y prime. So let's replace y prime with dy dx. And now let's put all the y's on the left side and x's on the right side. So let's multiply both sides of the equation by dx. We now have e to the y minus 1 dy equals 2 plus cosine x dx. Now that we've separated the functions, we can integrate. On the left, when we integrate, we get e to the y minus y equals. On the right side, we get 2x plus sine x and plus c. Technically, there's a constant on the left side as well, but we just combine it to the constant on the right side. And at this point, we can attempt to solve for y, but it looks like since we have y in the variable and y down below here, it looks like we cannot explicitly solve for y. So we're done at this point. We've got an equation for the solution of this differential equation.